It's my pleasure to have Alex Cohen as a speaker at our seminar. He's probably the youngest speaker so far. He will start PhD this fall. He'll do his PhD at MIT, and he already has impressive results. And he'll talk about one of them, joined with Guy Moshkovitz, about tensor ranks. Thank you, Alex. You should unmute yourself before you start talking.
Okay, can we still see everything?
Yes, it's good.
Okay. Yeah, thank you so much. It's a pleasure to be here. Feel free at any time to interrupt with questions. And yeah, I'm going to talk about a few notions of tensor rank and how they compare to each other. Okay, so to start off, the basic object we're going to be talking about are tensors. So in some way, the most native view are a higher dimensional generalization of matrices. So an n by n by n tensor, you can think of as an n by n by n grid of numbers. So this is an example. It's a very nice tensor. And there's many other ways you can view a tensor. One perspective that's going to be useful for us is viewing a tensor. And by the way, right, you can have higher order tensors as well, but we're going to be focusing on order 3 tensors, which is like 3-dimensional grids. So the other perspective we're interested in is as a tensor as a trilinear form, right? So if you have a matrix, you can turn it into a bilinear form by sort of, if you give me two vectors x and y, I can put x on the left and y on the right, and I can give you a number. The same way for a tensor, if you give me 3 vectors x, y, and z, I can give you a number. And the way I do that is I just make a polynomial out of them. And the coefficient of xi, y, j, z, k is the I, j, k entry of the tensor. So for example, this tensor with the ones and negative ones, the trilinear form it corresponds to is the determinant form, if I wrote it correctly. It should be the determinant form. But anyway, it's the same object. And throughout, right, we're always going to be, fixing bases for all of our vector spaces, so we can take coefficients and all of that. Okay. So, right, so what we're interested in here is a notion of tensor rank. And, an important distinction to notice is that tensor rank is really very different from matrix rank in the following way. So matrices, right, as objects, what makes matrices so simple is that they are classified up to a change of basis by just one number, which is their rank, right? So if you have any matrix, you can always, right, by multiplying on the left by some interval matrix B and the right by some interval matrix C, you can put your matrix into the form where it has like, R ones in the diagonal and everything else is zeros, which is like a standard form. And the number of ones on the diagonal in that standard form is the rank of the matrix, right? So, there's a million ways you can define the rank of a matrix, but it's all measuring the same underlying thing, which is this equivalence class of the matrix. And it doesn't matter what definition you choose, and there's really only one right way to do it. Okay, but tensors are a very different story. For tensors, there's uncountably many non-equivalent tensors, right? There's no standard form like this, in an analogous way to matrices, which means that if you want to define some notion of tensor rank, right, there's going to be several different non-equivalent choices. And it turns out that there's no one best notion of tensor rank that captures everything people could want from a notion of tensor rank. There are several different notions that have different applications. So, it's sort of a basic distinction. Tensors are not as ubiquitous in math as matrices. They're sort of more niche, but they capture a lot of combinatorial and theoretical computer science structures that end up being very important. And tensor
Alex,
rank
can I ask you a quick question?
Yeah.
So also generally we ask questions like that. So I hope it's okay with you.
Yeah.
Should we think about coefficients coming from R, C, or what is the choice? Or it doesn't matter?
No, that's a great question. So in general, it is actually going to be a pretty important question for us where the coefficients come from. in general, there's sort of, one part of the story, it's going to be in an algebraically closed field, and another part is going to be in a finite field. And we're going to sort of have to worry about how those interact.
Okay, great. Thanks.
Okay, right. So before I tell you what we are going to talk about, I'm just going to tell you what we're not going to talk about. So when people say the words like tensor rank, they're usually referring to a particular notion, which is especially useful in theoretical computer science. So this notion of tensor rank, it takes a value for like an n by n by n tensor. It takes a value between 0 and n squared. It's extremely difficult to analyze, and it measures like the arithmetic complexity of the tensor in some sense. We're not going to talk about this. We are talking about a family of notions quite far from this one, and which sort of capture something else about the tensor. So the family of notions we're interested in, they all take values between 0 and n for an n by n by n tensor. Okay, so now let me tell you what we are going to talk about. So the first notion of tensor rank we're interested in is the slice rank. So the slice rank comes from combinatorics. It was introduced by Terry Tao in the context of the cap set problem. So in his blog post, he gave a reformulation of the Ellenberg-Heisfart bound. I hope I pronounced that somewhat correctly. Right. So he reformulated that proof by introducing this concept of slice rank, and it's useful in an analogous way to matrix rank. In that, specifically for this cap set problem, okay, the game is to try and prove you can't have a very big, combinatorial object. You argue that if you did have a big object of this sort, then the slice rank of some tensor would be very large. But then also you compute, explicitly somehow that the slice rank of that tensor is not very large. And then by estimating the slice rank in two different ways, you get a bound for your combinatorial object, which is analogous to how matrix rank is used often in combinatorics. And so this was introduced in 2016. But as we'll see, actually, a lot of these notions, when they were first formulated by their current name is not always the first time people were working with them. People have actually been working with the same ideas for a long time under different names. So don't take the dates, too seriously. Okay, analytic rank is another notion. It comes from higher order Fourier analysis and was introduced by Gowers and Wolf. And this notion applies, so by the way, slice rank works over any field. Any field you have, it's a combinatorial notion. It works no matter what. But analytic rank is only defined over finite fields. And where this notion comes from is you sort of, right, as we said, you view your tensor as a function that happens to be a trilinear function. You just view it as a function. And the analytic rank sort of measures the bias of this function, which is some measure of how far the distribution of the outputs are from uniform, right, in some way. And the third notion we're interested in is geometric rank. Geometric rank comes from algebraic geometry, and it is a generalization of the codimension of the kernel definition of matrix rank. It applies only, so analytic rank only applies to finite fields, and geometric rank only applies to algebraically closed fields, right? And the reason for that is because it's based on algebraic geometry. So the basic, manipulations we want to do to make geometric rank have reasonable properties only work at all over algebraically closed fields. Okay, everyone got in the definitions?
Can you not define the geometric rank by taking the algebraic closure of the field that you start with?
Yes. So if you give me a tensor over, F5, I can tell you geometric rank by taking the algebraic closure, and that's what we will end up doing. Okay, so the main result, I'll spoil the show a little bit. These notions are all essentially equivalent. So these notions all sort of created this work, and what we ended up showing is that for 3 tensors, all of these notions bound each other by linear factors. So, it's definitely not obvious in the definitions, but it turns out that these 3 very different, seeming notions of tensor rank are actually all measuring the same fundamental quantity. All right, so now I'm going to talk about slice rank. Okay, so the slice rank, it generalizes the following definition of matrix rank. So a matrix has rank 1 if it's the outer product of 2 vectors. And then, okay, once we know what the rank 1 matrices are, we can then define the rank of any matrix by saying the rank is the minimum number of rank 1 matrices so that we can write it as a sum. So, right, the matrix has rank 5, less than or equal to 5, we can write it as a sum of 5 rank 1 matrices. So that's why I say it's a combinatorial notion. It's sort of, right, it's like the minimal way you can write it in this form. Okay, So how do we generalize this? Well, first we have to say what a slice rank 1 tensor is. So we say that a tensor has slice rank 1 if it's the outer product of a matrix and a vector. Right, so for this example, we have this matrix with the 1s and the 2s and this other vector, and right, we can take their outer product and we get some new tensor. And so the reason it's called slice rank is because we have these sort of like matrix slices that are all linear multiples of each other. So this is a slice rank 1 tensor, and we define the slice rank of any tensor to be the minimal R, so that we can write it as a sum of R slice rank 1 tensors. Okay.
And I guess here you maybe want to stress that they don't necessarily have to come in this order, this matrix, and I mean it can be along any direction, right? If you
exactly. So right, that's this. Yeah. Okay. So, right, that's exactly right. So that's exactly what makes this notion so tricky to analyze. So that's what makes it so much more difficult than matrix rank. Is that there's 3 different ways you can take the outer product of a matrix and a vector. So this is particularly nice to look at from the trilinear form perspective. Right, from the perspective of trilinear forms, the operation of an outer product is very simple. It's just a product of polynomials. So in this example on the left, right, so in this case, right, the matrix is a bilinear form in the y and z, and the vector is a linear form in x. And we take the product to get this trilinear form. And right, we can choose any variable to be the linear form. So we could choose a linear form to be x and the bilinear form to be y and z, the linear form to be y and the bilinear form to be x and z, right, etc. It's just we have to choose one to be the linear form. And there's 3 different choices, and there's 3 very different ways to make a slice rank 1 tensor. And what makes this notion so difficult is that when you have a slice rank 7 tensor and it has pieces from each of these axes, they all get messed up and they all get mixed up together. And so that's what makes it so hard to actually figure out what the slice rank of a tensor is. Yes, okay. Okay, so that is slice rank. Now we're going to talk about geometric rank. Okay. So geometric rank generalizes, rather than this combinatorial definition, it generalizes the geometric definition of the rank of a matrix. So given a matrix, you can view it as a linear map, right? So it takes in a vector and outputs a vector, and it's very natural to look at the kernel, which is the set of all input vectors that give the output 0. This kernel is a linear subspace of Fn. Okay, very nice subspace. And the rank of the matrix is the codimension of the kernel, right? So it's like the, number of degrees of freedom you have, outside of the kernel. So for a tensor, okay, if we want to define the geometric rank of a tensor, I have to tell you what the kernel is. So in order to do that, we make a choice. So I'm going to, so you give me a tensor T, I'm going to make a bilinear map. So not a bilinear form, but a bilinear map that takes in 2 vectors and outputs another vector. And it's bilinear in the inputs. So just to be perfectly explicit, if T1 through Tn are like the matrix slices of T, right, the slices from the last slide, then the bilinear map is the function that takes in x and y and outputs the vector whose coordinates are these n different bilinear forms in y and x. So this gives, right, the function that takes in 2 vectors and outputs a vector. And now I define the kernel to be the set of all 2 input pairs whose image is 0, right? That map to 0 under this bilinear map. And now, instead of being a linear subspace, this is going to be some algebraic variety in F2n. Right? It's not going to be linear anymore. But it still has some codimension, and so we define the geometric rank of the tensor to be the codimension of its kernel. Okay. So just to give an example, this is the same tensor we had on the first slide. It's the determinant tensor. So it's the function takes in x, y, z, and outputs the determinant of the matrix that has those as columns. Right? As we all learned in linear algebra, this is a multilinear form, so we're good. It's a tensor. Okay, the bilinear map that we get from this tensor, right? What is it? Well, it's the function, right? The image of x and y should be the vector such that when you dot that with z, you get this determinant. And it's exactly the cross product. So the t of x and y is x cross y. Okay, so what is the kernel? So the kernel is going to be all of the pairs x and y whose cross product is 0. All right, this is not, we can describe this space explicitly, and then we can just compute its dimension. Its dimension is 4. The reason is that we have, 3 degrees of freedom to choose x, and then once we've chosen x, there's 1 more degree of freedom to choose y. So that's a total of 4 degrees of freedom, so it's a 4-dimensional space. And because the ambient space is 6 dimensions, because there's, 3 for x and 3 for y, the codimension is, 6 minus 4 equals 2. So that means that the geometric rank is 2, which is less than the maximum value of 3. So this determinant tensor does not have full geometric rank. On the other hand, you can prove that it actually has full slice rank. The slice rank is 3. There's no way to, slice it up with only 2 pieces. So these two notions are genuinely different in general. Okay, now we're going to talk about some basic properties of the geometric rank. So first property, right, as you may have noticed, right, in order to even define the kernel, we had to make a choice, which was right, we had to choose that, like, we're going to map from x and y to z. We had to choose which coordinate was the target and which 2 were the inputs. And so there's 3 different choices we can make. We could choose x and y to map to z, or x and z to map to y, or etc. And right, if those different choices will lead to genuinely different kernels. But it turns out that any choice, right, any of those 3 choices of how to slice the tensor will give you the same geometric rank. So no matter what, the kernel will have the same codimension. And this theorem is analogous to the fact from linear algebra that the dimension of the row space and dimension of the column space of a matrix are equal, which is actually not a trivial theorem. Okay, so fact number 1, the geometric rank and the slice rank both live in the range 0 to n. So they're, at least comparable in that sense that they live in the same range. It's also true that geometric rank is bounded above by slice rank. So we're gonna prove this by example in the next slide. Right. So if you have a small slice rank decomposition of your tensor, then you can also know that the kernel has small codimension. Okay. Geometric rank and slice rank are genuinely different notions. We saw this with the determinant tensor. Okay. Right. Now we're going to explain why geometric rank is bounded above by slice rank. Okay. So I've just written here a tensor T along with I've given it a slice rank 2 decomposition, right? So this first piece, the linear form is in X, and the second piece, linear form is in Z. These are both slice rank 1 pieces, so T has slice rank at most 2, and actually equal to 2, but at most 2, because we've written the decomposition. Okay, so the bilinear map is the map, it's the vector, right? Each of whose entries is a bilinear form, and like the first entry is the coefficient of Z1 in this polynomial. The second entry is the coefficient of Z2 in this polynomial, and the third entry is the coefficient of Z3 in this polynomial. And the kernel is a set of all inputs x and y that give you the 0 vector, where these 3 bilinear forms all vanish. Okay, but we notice that if x1 plus 3x2 minus 4x3 vanishes and x1 y2 plus x2 y1 vanish, then actually all 3 of these entries have to vanish. And that's because every term here has one of these 2 functions as a coefficient, right, as one of its factors. And that's no accident. That's because we chose this linear form in X and this bilinear form in X and Y to each be factors of the two parts of T. So the key idea here is that if you have a slice rank 1 piece, it's always going to have one factor that doesn't involve Z. Right? It could be the linear part or it could be the bilinear part. It's always going to have one part that doesn't depend on Z. And so for each slice rank 1, right, for each piece of the slice rank decomposition, we choose one equation, right? The equation we choose is one that doesn't involve Z, or one of the ones that don't involve Z. And then if all of those R equations vanish simultaneously, for sure X and Y are in the kernel. Okay, so now we've found explicitly R equations such that if we line the common vanishing set, then we're in the kernel. But by algebraic geometry, if you have, right, the vanishing set of R equations has codimension at most R, right? The largest possible codimension it could have is R. And because we found a codimension at most R subvariety of the kernel itself has codimension at most R, right? It could, at worst, it's bigger. Okay, this make sense to people? Cool.
It's good, yeah.
Okay.
Yes,
so
maybe one thing that you could spend on is a little bit more on how you write this T of xy as a bilinear map. But I mean, it doesn't really matter for your proof, but maybe it would be good to just say where these coefficients come from.
Yeah. So in this particular example, right? So to find like the first entry of this vector, you look at the coefficient of z1. Okay, so this has two parts. From the left-hand side, we have x1 plus 3x2 minus 4x3 times y1. Okay, that's here. And then we have z1 times x1 times y2 plus x2 times y1. That's here. So the entries of the bilinear map come from the coefficients of the zi's. Okay, so here's a theorem, which we proved. Slice rank is bounded above by twice the geometric rank. So in other words, if the kernel has small codimension, the slice rank is small. So before this work, we didn't know if there was any upper bound for slice rank in terms of geometric rank. So we thought it might be possible that the geometric rank could be like 2 and the slice rank could be unbounded. But it turns out that's not possible. They're linearly, right? There's an upper bound, and in fact, there's a linear upper bound. And in this business, the linear upper bound is essentially equivalent, right? We're dealing with big numbers generally. So linear upper bound is generally enough to say that they're equivalent notions. This theorem illustrates that slice rank and geometric rank are actually measuring the same underlying quantity in some way. And they're two very different perspectives on that quantity. So slice rank is this combinatorial notion, and geometric rank is this very geometrical notion. They just, you can think about them in very different ways. And that's always a very useful thing in math, if you have two very different ways of thinking about the same quantity. So in particular with this cap set problem, right, it's particularly nice to, right, you bound the slice rank above explicitly using these, this decomposition, and then it turns out that you've also bound the geometric rank. And in general, the geometric rank sort of has nicer theoretical properties. So for instance, it's like additive under direct sums, which slice rank, it's not known if that's true. So if you prove a theorem using geometric rank, then it follows as well for slice rank. And in fact, okay, we're going to do these.
Actually, can I ask you one question here?
Yeah.
So for that particular application, like for this cap set application, because I don't remember now, but my feeling is that this constant 2 there may be actually important, right? So if instead of bounding it from above, you somehow bounded geometric rank and use this bound, would it still give something non-trivial for this or not? Because there, as far as I remember, everything was linear, right? So this bound, the bounds were somehow linear, and I'm not sure if this 2 would cause problems. I don't know if my question makes sense.
I think it will work.
Yes. Okay. So you think that even with 2, it would give something?
It's my.
Okay.
Yeah, I do not know exactly for that case. In general, geometric rank is less. So there might be some hope of getting a better bound. But that's a good. I'm not sure if that specific case, if the 2 matters. Okay. But okay, one case which I tell you it is useful is we're going to use this theorem as a tool in order to relate slice rank and analytic rank, which is somehow the combinatorially more significant problem is to relate slice rank and analytic rank. And so this theorem is a tool for us in order to do that. Okay, so a couple of comments. So this theorem, so under about the question of the fields before, which is a very important question for us. This theorem applies over algebraically closed fields, right? So if you give me a tensor T, when I compute the geometric rank, I'm viewing it over the algebraic closure implicitly. And this, what this theorem does is it will, right, if we know it has small codimension, we're going to build a small slice rank decomposition over the algebraic closure, right? Not over the field that the coefficient started in. And also, okay, so another note, we have since extended this to higher order tensors. So really, so slice rank applies to higher order tensors, but it's not the right generalization in this context. The right generalization is this thing called partition rank, which I'm not going to talk about in detail, but it's somehow the right analogous notion for higher order tensors, and geometric rank is linearly equivalent to partition rank for higher order tensors. And the proof is it has the same core ideas, but it is substantially different in some key ways. Okay, so that's geometric rank. Now I'm going to talk about analytic rank, which is the third notion of rank we're interested in. And by the way, I'll mention we're talking about these three notions, but there actually are some other ways to get at it too, and they're also all equivalent. So right, there are some other notions that are going to be equivalent to size rank. Anyways, these analytic rank is the third one that we're interested in. Okay, so right, as I said before, this notion is defined over finite fields. So you give me a tensor T, the analytic rank is okay, so first ignore the log term. Okay, let's just first look at this term. Okay, so chi is a non-trivial additive character. So if the field is a prime field, then you can just think of it as, the T of x, y, z is going to be some number z mod p, and then we put that onto the unit circle, right? We map to e to the 2 pi I times the output over p. And so then, right, for every output of the tensor, we can then map that onto the complex unit circle with this non-trivial additive character. And this expected value is a measure of the bias. So let me see, I have a picture. Yeah, okay, so it's a little bit goofy picture, but the bias is the expected value of the outputs on the unit circle of the tensor, right? So this bias is, it's a pretty natural thing to look at if we view the tensor as a function rather than as like, right, this definition works just well for a function as well as it would work for a polynomial. Now it turns out, even though it's not obvious, that the bias is always going to be a real number in between 0 and 1. So we take its log, with the base of the log being the size of the field. It turns out that's the right way to normalize it somehow, but that's a quantity which decreases as the bias increases. So the more biased, the smaller the analytic rank. And okay, one good reason to take this log is that it turns out the analytic rank of an n by n tensor lives in the range 0 to n, like slice rank and geometric rank. So it lives in the right range at least. It is also bounded above by slice rank, just like geometric rank. So if you know that you can decompose your tensor into a few slice rank 1 pieces, then it also follows it's going to have a large bias. Right, and this notion, as I said, it comes from additive combinatorics and higher order Fourier analysis. So in that business, right, there's a general interest in the bias of functions. And so this is just what happens when we apply the notion of bias to a trilinear function. Okay, here's a lemma, which is not obvious, but it's also not too hard to prove, is that there's a formula for the analytic rank in terms of the size of the kernel of T. Okay, so what does this mean? So this kernel of T sub f thing, right, so the kernel of T is some variety over an algebraically closed field, right, the closure of f. But this is just referring to the number of points in that kernel which have coordinates that are in f, right? So it's literally, because the finite field, it's just a number of vectors x and y such that T of x, y equals 0, right? That's this. It's just a number. It's a point counting. So then the analytic rank is 2n minus the log of that number. Okay, and
so for this thing, we think of this T as, again, this bilinear map, right?
Exactly.
Yes.
Yeah.
Mm-hmm.
We think it is a bilinear map.
Okay.
Right, and so it turns out that this. Okay, so let's just think about the case where kernel of T. I'm going to explain this in more depth, but think about the case where kernel of T is a linear subspace, right? So let's say a linear subspace of dimension d. Then the number of f rational points is exactly size of f to the d, because it's isomorphic with f to the d. Okay, so then the log base f of the size of the kernel is just d. And then the analytic rank is 2n minus d, which is the codimension of that linear subspace. Okay, so what that example illustrates is that this analytic rank is like it's like a finite field version of the codimension. Right? This point counting is like a finite field version of taking the dimension in some way. And exactly how that works is important, but right, in some way it's an analog of the codimension. And in fact, historically, right, geometric rank was defined in order to be a smooth version of analytic rank. So analytic rank came first, and then geometric rank was defined afterwards as like a smooth analog.
By smooth, you mean for infinite fields, or like for C? Or by smooth you mean an analog for C, or?
No, I just meant like more geometric than like counting. Not literally smooth in the geometric sense, but just smooth like we're dealing with, varieties rather than counting points.
Okay.
Alex, if I take field extensions, then does the expression on the right-hand side converge to the geometric rank?
That is a very good question. So the let me remember exactly how it works. The lim inf will be equal to geometric rank. However, in general, you can have subsequences that converge to larger values.
I thought there are some general facts from algebraic geometry that basically the size of your variety in terms of number of points is to first order given by its dimension.
Yes. Let me think for a moment. It's right. That is.
So you phase. So Alex, the lim inf refers to if you take different primes, but different characters. But if you fix your character and you take a large enough algebraic extension,
right,
then the top dimensional components are going to be defined over your extension, which means that you could do, Lang-Weil point counting works exactly as you would expect. So the answer is yes.
Yeah. Yes. Okay. Yes. Okay. So people have been working in the past on how slice rank and analytic rank relate to each other. So people were actually talking about this even before slice rank was literally written down. So a bound for slice rank in terms of analytic rank, it fits the prototype of an inverse theorem. And the reason is that, right, so if the analytic rank of T is small, that means that T is biased. Okay, and so the question is, given that T is a function that has some bias, can we conclude that it's structured? Can we explain that bias by decomposing T into a few highly structured parts? And so in some sense, trying to bound slice rank in terms of analytic rank, and more generally partition rank in terms of analytic rank, is like a simplest case of the inverse conjectures for the Gowers norm. It's like the case, if you know what that is, I'm not going to talk about it in depth, but it's like the case where the input functions are themselves polynomials. Okay, so the first bound of this sort was by Green and Tao, and it was later refined to work over more fields by other authors. And they proved that partition rank, which is this higher order generalization of slice rank, is bounded by a function of analytic rank. And this was really a qualitative theorem that function had Ackermann type growth. So it was really not a quantitative theorem. Later, Haramaty and Shpilka showed that the slice rank is bounded by analytic rank to the fourth power. There should be a constant there. Some constant times analytic rank to the fourth power. This is a way better bound for the specific case of 3 tensors, which is what we're talking about in this work. Then, very recently, Milosevich and Janzer proved that partition rank is bounded by a polynomial function of analytic rank for all k, so for higher order tensors as well. And it's been conjectured by several authors that the slice rank is bounded by a constant times the analytic rank. And in fact, that the partition rank is bounded by a constant times the analytic rank. So these quantities are in fact linearly related. Okay, so this is our main theorem. We proved that this is actually true for 3 tensors. We proved that the slice rank is bounded by a constant times the analytic rank. And notice that, right, there's this issue of fields, but the fields work. We take the decomposition over the right field. So if you give me a tensor, you've computed its bias, found it has a large bias. I can then assure you that it will have a slice rank decomposition into not too many pieces, and the number of pieces is like linear in the log of the bias. All right, so best pair bound, as I said, was slice rank is bounded by the fourth power of analytic rank. And the techniques we use are very different from the usual techniques for this problem. We are using local ideas in algebraic geometry rather than this sort of global analysis, which is the usual thing. So some remarks. So Adeprasito, Kashtan, and Ziegler independently proved the same result, building on work of Schmidt. This was released like a couple months ago. And we have, so by the way, this work of Schmidt, it was sort of, just to clarify, is like, he was working on some other problem in number theory, and this is sort of like buried into one of his papers. It turns out that the core ideas were buried in this other paper on number theory, and we weren't even aware at all of his like notion of Schmidt rank, which is what they're building off of. So it's pretty interesting that there is these ideas that showed up in the context of number theory in a totally different way. I think it wasn't really known to the community that Schmidt was working on these things in another context. So we've since generalized this work to higher order tensors. So we've related partition rank and analytic rank with a linear bound over large enough fields. And it seems that the work of Schmidt does not generalize as well to this higher orders, as far as we know. For working with finite fields, it does work for geometric rank and partition rank, but we think not as well for partition rank and analytic rank. Okay, but we're focusing on 3 tensors. Okay, so now we are going to prove the theorem. So I think I can just sort of talk about the proof outline, and then we can have a little break. Okay, so here's the outline. So we start with analytic rank. Right, you have a tensor. You found that it has a large bias. You say you want a small slice rank decomposition. Okay, what do we do? Well, the first step is to prove that if it has a large bias, then the geometric rank is small. Right, so if the analytic rank is small, then the geometric rank is small. The way we do this is by, okay, sort of like one direction of this. Okay, so the way we prove this is by saying that if the kernel has a small dimension, then it also has not too many points. So we sort of prove it in like the other direction. We prove if the geometric rank is large and the analytic rank is large. So this, right, so Yifei is talking about the Langevin bound, which says that the number of points is really like basically equal to the codimension. This is like one direction of that inequality, which is by far the easier direction and applies in greater generality. Okay, so now we've proven, we have started with large bias, and now we've proven that in fact, if you view your tensor over the algebraic closure, then it, right, the kernel as a variety has large dimension. It's a large dimensional variety. Okay, what do we do now? Well, we take just like some point, like a generic point basically, on that variety of the kernel, and we like look at derivatives near that point. We look at tangent basis derivatives, local things, and using those derivatives, we build a small slice rank decomposition for the tensor. Okay, and then we have found a small slice rank decomposition using a small analytic rank, using large bias. Okay, there's one issue here. Does anyone see an issue in this outline? Okay, I'll spoil it. The issue is with the fields. Right, we were talking about before. There's this thorny issue of the fields. So the problem is this GR to SR bound inherently works over the algebraic closure. Right. So the question is, how do we then build a small slice rank decomposition over the base field we started with? The way we do that is with this result from Dirksen that like came down to us from the heavens, which proves that in fact for 3 tensors, the slice rank is stable under field extensions. So right, if you take the algebraic closure, there could potentially be a smaller slice rank decomposition because you have more possible slice rank 1 pieces. But it turns out that if you have a small slice rank decomposition over the algebraic closure, then you also have a small decomposition over the base field. And that lets us complete the circle. And so we now conclude the small slice rank. Okay, let's take like a couple-minute break. Or maybe.
Great, yeah. There is also some question in the chat. I don't know if you have anything to say about that. You can take a look. But other than that, we can continue at 8 Moscow time.
Like, where are you? Where does the F2 restriction come up?
So that comes up in short Stipple. It's so, the 2 there is because the polynomials have degree 2. The bilinear maps.
Are there other methods of bounding number of points on varieties, like, I don't know, Langevin type approaches that, does that also encounter the same type of F2 issues?
Yeah, so it's a real issue. The 2 there comes from, so I'm going to talk about this in more depth, but so in Schwarzschild, there's sort of like 2 factors. There's one factor coming from the dimension of the variety, another factor coming from the degree of the variety. And the 2 there comes from the degree of the variety being large. And so that shows up in Langevay too, right? It's actually in Schwarzschild, it's much easier to deal with that than in Langevay. It's actually much worse because there's like a dependence on the ambient space, which Schwarzschild, the version of Schwarzschild we use, doesn't have. So it's like, okay, it's a question of how you measure complexity of your variety, which sort of has to be a factor in the bound on the point counting. And because we're dealing with the equations that are cutting out our variety have degree 2, we sort of, at least as far as I know, you sort of have to have that factor coming from the degree, and that factor is what gives this restriction on not working over F2.
So potentially this linear dependence could be false over F2.
Yeah.
So this case is also not covered by this Adiprasito and others paper. Or do they prove it only for large enough fields? Or?
I believe so. I believe that they also don't cover F2, although I'm not. I don't have that like.
Yes, it's the same issue with their paper too.
Right, for higher order tensors in general. Sorry.
There's an analogous situation with inverse theorems where, if you work over 2 small fields, then the naive statement of inverse Gowers theorems fail. And in fact, there are counterexamples, which is what leads to all these non-classical polynomials. So it'd be interesting if something similar like that comes up here as well.
Oh, that is interesting. That might be.
Yeah, so there are these papers that are titled something like the inverse Gowers conjecture is false, which means basically that the naive formulation, just using polynomials is false, as stated. But then you need to introduce extra objects.
All right, that's interesting. Yeah, I guess that. Right, because I work on higher order tensors too. It has even stricter conditions on. Look, we need a large field, so maybe there is something else going on for smaller fields. Yeah.
I would say that the difference here is that we're talking about tensors still, so we don't really run into the issues of polynomials where there can be non-classical polynomials. We're only talking about tensors. So there's still hope that over F2 the linear bound would still hold. There's just the issue of non-classical polynomials it doesn't exist when we're talking about tensors.
So yeah, seems like the break was gone with in the discussion. So if it's okay for you to continue, then I guess we can.
For sure. All right, let's continue. Okay, so we're going to start with this AR to GR step. So this is the small proposition. For a 3-tensor T over a finite field, the geometric rank is bounded by this constant times the analytic rank. Okay, and the tool that we use to prove this is this generalized Schwarz-Stipple lemma. So the Schwarz-Stipple lemma says that if we have a variety and it's cut out by pretty small degree equations, degree less than or equal to D equations, then we have this bound for the number of F rational points on it, right? Meaning points on the variety that are actually in F. And so there's sort of I'm going to talk about this bound more in the next slide, but there's this factor of coming from the dimension. So like if it's linear, this is tight, and there's this other factor, which sort of comes from the complexity. And then the proof, it's 3 lines. So we have our formula for analytic rank in terms of the size of the kernel. We insert our upper bound for the size of the kernel using Schwarz-Stipple, which has the dimension of the kernel as a factor. The 2 here comes from the fact that the kernel is cut out by degree 2 equations, right? So it's cut out by this system of bilinear forms. And then we get that if the geometric rank is large, the analytic rank is large too, with the caveat that this doesn't work if the size of the field is 2. And okay, this is just a cartoon of some points, some F rational points on a variety.
I think it would be good if you go just a little bit slower with all this, because I think not everybody is well trained in algebraic, algebraic things here. So.
Yeah.
I mean, you have time, so you shouldn't. There is no need to rush.
Yeah. Right. I think probably the trickiest part is Schwarz-Zippel, and so I have a whole slide on that. So Schwarz-Zippel. Okay, so what is this saying? So first, to understand it, okay, let's take one extreme, which is when the variety that we're talking about is a linear variety. So if we have a linear subspace, it's cut out by degree 1 equations, and then in fact, the number of points on it, because it's isomorphic to f to the d, is exactly the size of the fields of the dimension of the variety. And so Schwarz-Zippel is tight for linear varieties, right? D is 1, and so we get equality. Right, and this is sort of like the motivating case. Okay, so I think how you should read this. So this d to the codimension v term, right? What this really is a measure of is like the complexity of the variety in some way. So what this really should be is this quantity, the degree of the variety. So the degree is this like miraculous definition from algebraic geometry, which is really the appropriate way to measure complexity for many circumstances. And so what's going on here is that there's sort of this when the complexity of the variety is very large, the lemma stops being useful, which it sort of has to, right? So if you think about an example, if you have any subset of Fn, because it's a finite, right? Because it's a finite field, any subset is finite. So any subset is also, right, an algebraic variety. But the thing is, you're going to need pretty large degree equations to cut out a finite subset. So if you have a subset of size of s, then you're going to need degree s equations to cut it out. And its dimension is going to be 0. So Schwarz-Zippel is going to give you this bound size of s is less than size of s to the n, which is not a very good bound. Okay, what's going on here is that this complexity term is exploding, even if the dimension term is small, right? And so you really, right, the complexity term is extremely important because, right, it's totally natural that if you describe a set with algebraic equations, the only way that you could algebro-geometric notion of dimension could actually be useful in controlling the number of points is if the complexity is pretty small in some sense. So, right, you should think of this as complexity, and then it's something we have to prove, which we do prove, that the complexity is bounded by d to the codimension. Okay, so that's, I don't know, it's not obvious, at least to me, that if the codimension is small, the complexity or the degree is small too. But it turns out it's true, and that's actually really important for us, that if the codimension is small, then you get a good control on the complexity. And for us, d is always 2 because we're working with these bilinear functions. Okay, any questions about Schwarz-Zippel? It's really...
Maybe it's a good idea also to mention, just briefly mention this, what is the codimension V and dimension V? I don't know.
Oh, yes. Okay, right. So V is, okay, so for instance, with the potato chip, right, potato chip is like the variety V, then the dimension is 2, because it's a 2-dimensional potato chip, and the codimension is 3 minus 2 is 1. That's the number of remaining directions. So, right, that f to the dimension of V is like, what would happen if it were a linear subspace, and then the codimension, right? It turns out that if you have the smaller the codimension, the smaller the complexity, and that bound, right? That d to the codimension v bound that comes from this Bézout inequality. That's sort of where that comes from. Okay, cool. Right, we sort of, for us, this sort of, I think we sort of took this for granted because it's sort of a, well-known and, often used lemma, but it's actually very core to the proof, right? We wouldn't even be able to get started without this, because this is how we relate this algebro-geometric notion of dimension to the point counting notion of analytic rank. Okay, so now we're going to move on to proving that geometric rank small implies slice rank small portion. So now we have something that has a kernel that has small geometric rank. So a small codimension, large dimension. Okay, so here's a lemma, which is really sort of it captures sort of the core ideas of the proof. So Okay, so there's a bunch of words. I'm going to try and explain it. So if you have, okay, this is a little cartoon on the right. So this yellow thing is like a cartoon for the variety of rank R matrices. So the ambient space is all of the possible n by n matrices, and the yellow part is the matrices that have rank, I don't know, 3. Okay, then this black point is some particular rank R matrix A. And the blue subspace is a tangent space to the rank R matrices at A. Okay, so the tangent space, right? I mean, I'm not going to, formally define it, but it's what you think it is. It's the tangent space. And so what we're doing here is we have this tangent space, which is a linear subspace of the set of matrices, right? Because the varieties in the set of matrices, the tangent space is a linear subset of the space of matrices, and we can view a linear subspace of matrices as a tensor in and of itself. And when we do that is we take a basis for that linear subspace, and that's just going to be some finite number of matrices, right? So if it's a k-dimensional linear subspace, then we get k matrices from taking a basis. And we make those k matrices like the slices of our tensor. So we can turn a linear subspace of matrices into a tensor by taking matrix slices. So this is just, explicit formula for the trilinear form we get by doing that. Okay, so right, that's okay. So hopefully it at least makes sense what this lemma is saying now. Is that right? We obtain for every rank R matrix a linear subspace of matrices, which is the tangent space to the rank R matrices, and then we can compute the slice rank of that linear subspace, and it's pretty small if R is small. And this is really, right, this lemma is really where we get our slice rank decompositions from. At the end of the day, what we're going to be doing is finding big linear subspaces that are sort of coming from tangent spaces to these rank R matrices. So when I was talking about that whole thing about derivatives and tangent spaces and local nature, this is the lemma where that comes in. Okay, so to be explicit, what is this tangent space? Well, I can describe the tangent space for you very explicitly. Say we have a rank R matrix A. Okay, then the tangent vectors are like the velocity vectors of curves on. Okay, so by the way, MR, this MR notation, that is the variety of rank R matrices. So this is like a subset of all the n by n matrices, and it's a subset of those that have rank R. So it's cut out by like the R plus 1 by R plus 1 minors. Yeah. Okay. So a velocity vector, right? So the tangent space consists of all of the velocity vectors through A, coming from curves on the variety of rank R matrices. This definition isn't what we actually use in the proof, but it's a nice way to think about it. And so if we have some curve through A lying on MR, you can parameterize that by saying, right, any matrix in MR, because all of the rank R matrices are related by change of basis, you can write any rank R matrix as B times A times C for some matrices B and C. Okay, so we just write like the matrix at time t as B of t times A times C of t, where B and C are the density matrix at time 0, and these are just n by n matrices. Then the velocity vector is like the derivative of this curve at time 0, and by the product rule, it's like B prime of 0 times A plus A times C prime of 0. Okay, and this is in fact the tangent space. So it is it's the collection of all matrices that can be written as B times A plus A times C. Or in other words, right, one matrix which is formed by rows coming from the row space of A, plus another matrix whose columns come from the column space of A. And that is the tangent space. And by the way, this first line is sort of where we use the fact that A has rank, right? So MR, this is sort of a subtle point, but MR is the matrices that have rank less than or equal to R. And we need A to have rank equal to R. It can't have rank less than R. And this is where we use that, is that we can write any matrix in A as B of t times A, C of t. Okay, anyways. Right, so you can view these as a linear combination of the rows plus linear combination of the columns. So for explicit example, okay, this is a nice rank 2 matrix. It has these 2 ones to the diagonal. Any rank 2 matrix can be put into this form by a change of basis. And the tangent space is all of the matrices of this form. right? Because this B times A thing is how you get, right, anything in the first two rows and then zeros below the first two rows. And then the A times C, you get anything in the first two columns and then zeros everywhere else. And so you end up with all the matrices that have a big like n minus r by n minus r block of zeros in the bottom right corner. And that's true in general for matrices of this form with rank r. Okay. So,
wait, so can you maybe give a little bit more time here? So now can you again say the part when you choose the bases, and how do we get from the rank of the matrix to the rank of the tensor? Maybe that would be
yeah. Great question.
Say it out.
Yeah. So, okay, right. So let's just take this example. So this example, right, the tangent space has dimension 12, right? 1 for each of the non-zero entries here, right? 4, 4, 4, 4. So we can take as a basis first a matrix that has a 1 in the top left entry and a 0 everywhere else. Then the matrix that has a 1 in the 1, 2 entry and 0 everywhere else, etc. So you could take as a basis the matrices Nij, where I is less than or equal to 2 or j is less than or equal to 2. Right? I and j don't lie in this bottom right corner. Okay, that's going to be like a bunch. It's a big dimensional subspace, right? The dimension is going to be something like what's going to be equal to right? It's 2nr minus r squared. So r times 2n minus r. It's a big dimensional subspace, and right, you stack those all up, and that forms the tensor. So actually, I can have a little picture, right? So for this specific case, the tensor it's going to have like these 12 slices. Right, 1 for each non-zero entry of that matrix. Okay, so now I'm just going to build for you an explicit slice rank decomposition of this tensor. Right, it's a very explicit object. We know what the tensor is. We can just write it down. So we can just write down a slice rank decomposition. So for the special case of A is IR, right, the trilinear form it corresponds to is this guy, this sum over all I and j in the top L of Zij times Xi times Yj. So you can view it as this, right? I've written it as like this in matrix form here, right? This Zij's is the same Zij's as the last slide. You put the Xi's on the left and the Yi's on the right. And the output is this number, which is the trilinear form. Okay, now this trilinear form, this is just a polynomial, and I can decompose it in this way. So it's going to be x1 times sum of Zij, Yj. Okay, that's x1 times the first row times the first column, plus x2 times the second row times the y. And so then, okay, so in general, this first rows of the xi times something, that will sort of cover the first r rows of the matrix, the first r rows of the matrix in this subspace. And then what's remaining is this lower right corner, the lower left corner, and we cover those by taking y1 times these two times the x3 times x4, and then y2 times these two times x3 times x4. And that same idea works in general. Okay, so you might not want to read all of this, but the point is just that there's really nothing crazy going on here. We just write down a slice rank decomposition using our explicit description of the tangent space. But really
is it actually enough for you just to think about this particular point IR, or do you really because you said that you'll fix one point, so cannot, or you're looking in the neighborhood of any point, or?
Yeah, it's totally enough to just look at IR because everything else is related by tangent basis.
Yeah.
So that's okay. Totally. Right, because what this little graphic is showing is that we're only using, right, remember the slice rank 1 pieces can come in 3 different flavors. And we're only using 2 of the flavors here. We're using the flavors that go like, this way and this way, but not flavors that come this way, right? In other words, the linear pieces are only in the x and y and not in the z. So really this is sort of, right, every tensor that can be sort of written in this way as these 2 flavors of slice rank 1 pieces is always actually like a tangent space of the rank R matrices. it's a pretty, right, they cover all the cases of these sorts of things. So it's, okay, so this is I'm done with the proof, and now I'm just going to talk a little bit more about that lemma, because it's an important lemma. Okay, right, so in the proof, the way this drives our proof is that we're going to use a large tangent space to the rank R matrices in order to build a small slice rank decomposition. It's inherently a local thing, right? We're looking at derivatives along this variety, right? Which is a very, very different way of thinking from how people usually are arguing about inverse theorems. So that's sort of why we're getting linear bounds, because we're looking at this local picture. And right, something I want to emphasize is that this lemma is like the simplest manifestation of some basic idea that has many formulations. So in our work on higher order tensors, we don't use this lemma at all, but it's the same basic idea. And in the Gajdan, Ziegler, Adipacito work, they don't use this lemma, but they use the same core idea. And in Spitz work, it's also the same core idea. So everyone who's getting linear bound for these things is using the same core idea. As far as I know, I haven't really seen any other basic ways of getting this relation between geometric rank and slice rank. It'd be cool to see some if people could find other ways of going about this. But everything I've seen uses the same idea. Okay, so this is just a short diversion to a classical result. So there's this theorem of Flanders, which is of a very similar flavor to what we just proved from the left side. So this theorem of, okay, and by the way, I know Avi Vigdersen was here recently. This originally we came to this lemma through Avi Vigdersen's survey on operator scaling, because I sort of remember that it was relevant somehow, and the proof of Flanders lemma was like the inspiration for this lemma. So Flanders lemma says if you have a matrix, each of which entry is a linear form. So suppose you have a matrix, each entry is a linear form, and okay, so it's maybe like a linear form in x1 through x5. For every instantiation of x1 through x5, the matrix has rank at most R, maybe most rank 3. Okay. Then this Flanders lemma says that there's matrices R and C, such that when you change basis by R and C, you put your matrix into this new form where, okay, it's still linear forms in each entry, and you have 0 forms in the bottom n minus R by n minus R block. It's really a similar flavor, and right, you can prove that you can use our theorem to rederive Flanders theorem over algebraic closed fields. So we can take the image of M by just looking at all of the possible matrices you get for all possible inputs. And because the entries are linear, this is a linear subspace of the rank R matrices. And the hypothesis is that every matrix in this subspace has rank R. But then, okay, a linear subspace has its own tangent space. So you write the linear subspace as its own tangent space at some particular matrix A. But then because L is contained in MR, you find that L is contained in the tangent space at any of its matrices of MR. And then those tangent spaces can be put into this form. So that's why L can too. So in retrospect, what's really going on in Flanders theorem is it's looking at a linear space, but it's really looking at tangent spaces. And so our lemma is like a nonlinear version of Flanders theorem. And if you specialize to this case of linear, right? If you specialize to the case of like a linear subspace, like this is the case of Flanders theorem, it's the same proof. So Flanders theorem is it's doing the same thing. Okay. So now we are in position to prove that slice rank is bounded by twice the geometric rank. Okay. So the first step is to view our tensor T as a linear subspace of matrices, right? So as I said before, this is like a one-to-one thing. We can always, right, we take those slices and we take their span, and that's a linear subspace of matrices. And you can go back and forth and you don't lose anything. Okay, so the second step is that so now we're viewing our tensor as like a subspace of matrices, and there's going to be different ranks, right? If you choose a point in the tensor, in the subspace, you're going to get different rank matrices. And we're going to look at the subvarieties for every different rank. So we're going to write by LR the collection of matrices in L that have rank equal to R, or less than equal to R, rather. So for instance, okay, in this example, this potato chip is like maybe the rank 3 matrices in L. and the three-dimensional ambient space is all of L. Okay, now it is a theorem which was proven in Guy and collaborators' original paper on geometric rank, that the geometric rank is equal to the minimum over all R of the codimension of this variety LR plus R. Okay, there's sort of like two factors to balance here. So the geometric rank is small if you can find a very large subvariety of matrices, all of which have small rank, and they're balanced by summing. So, okay, this is actually equal to the minimum over all R of this codimension, right? It's sort of it sort of makes sense, right? The geometric rank is small if you find this large subspace of matrices with small rank. And we just pick R so that we get equality. And in fact, we pick the minimum R so we get equality. Okay, so now it's a fact from algebraic geometry, which is really, okay, sort of taken for granted in algebraic geometry, but it's really core to what we're doing. And it, okay, I can talk more in a moment, but we pick some matrix that has rank exactly R, and we're going to pick it to be on the largest dimensional component, and we're going to pick it to be a non-singular point, large dimensional component. Okay, I haven't told you what non-singular means, but it's just like, you know, there's no like kinks at that point. It's like a pretty nice point. And okay, so we pick it so that the dimension of the tangent space to this potato chip is equal to the dimension of the potato chip itself, which is true for like most of the points. Okay, one thing that could happen that isn't depicted here is like you could have two you know, components to the potato chip. You could have like the two-dimensional part, and you could have like some little strand that's one-dimensional. So A always has to be on the largest dimensional component. Okay, so this blue tangent space is going to be dimension 2, just like the potato chip itself. And by the lemma, the tangent space at A, right, because the potato chip is a subvariety of MR, the tangent space at A of the potato chip is going to be a subset, a subspace of the tangent space at A of the rank R matrices, which is a much larger dimensional, you know, space of matrices, but regardless, it has small slice rank, as we showed, right? We slice it up not according to the, you know, large dimensional stacks, but according to the two other directions. And so, in fact, this subspace, which is a subspace of L, right? The blue tangent space is a subspace of L, right? That subspace has to have small slice rank less than or equal to 2R. All right, and notice actually there's many choices here, right? You could choose A to be any point on this LR, and you get a different subspace, all of which have small rank, have small size rank. Okay, now the next step is pick N to be a complementary subspace to this TA of LR. So here N is like, you know, going in the other direction, and the dimension of N is equal to the codimension of LR. Right, by the definition of codimension, that's how, right? It has to be, you know, dimension of L minus the dimension of TA of LR. And this N is sort of going to like control the error term. So what happens is because TA LR plus N equals L, you can think of it in terms of slices as like you get all the slices of L by stacking up the slices of this tangent space and then adding on the slices of L. And so the slice rank, as you might expect, it's sort of like, you know, it's subadditive under this operation of addition of subspaces, which is, you can think of as like adding on, right? You have like some stacked tensor and you stack up another piece, and then the slice rank is at most the sum. So slice rank is going to be at most the slice rank of this guy plus slice rank of this guy. The slice rank of this tangent space is at most 2 times R. And the slice rank of N, because it only has N stacks, it's at most codimension of LR, which is the number of stacks. And when we do that, we just take the decomposition where we just take the slices to be each, you know, each piece of N coming from like the basis. And then we break this 2R into R plus R, and we get slice rank is less than R plus codimension of LR, which is R plus the geometric rank, which is less than twice the geometric rank. So overall, we have the slice rank of L, which is the slice rank of the tensor, is less than or equal to twice the geometric rank. So to recap, what happened is we picked particular matrix in A on the large dimensional component, and we had many choices. And then using that, we got some large subspace of L, which has small slice rank. And we only need actually 2 of the axes to build the small slice rank. So that's in this picture, it's like the L bracket is coming from the tangent space part. And then because geometric rank, right, you have to have R is small and the codimension is small, the error term, which is sort of like to fill up the rest of the space to get to the whole thing, has to be pretty small too. And that is where you get the third flavor of slice rank from. It's from that error term. So overall, you get these all three flavors of slice rank, which is very important. You have to be able to get all 3 flavors because, right, you could have given me a vector of slice rank 1 or slice rank small coming from any of the different flavors. That would have slice rank, maximum if you just look at the other 2. And so the proof has to be able to build slice rank pieces coming from all the different flavors, which it does. All right, and importantly, it is actually important in the sequel that we can sort of build many decompositions. We end up taking like derivatives of different decompositions. I won't get into that too much, but that is like an important feature. Okay, so that proves that the slice rank over the algebraic closure is at most twice the geometric rank. Now all that's left is going back to the base field. So as we said, if you look at a field extension, the slice rank could decrease because you have more slice rank 1 pieces. But Dirksen proved that the slice rank is at most 3/2 times the slice rank over the algebraic closure. And the proof uses geometric invariant theory. It's totally unrelated to all the things that we did here. And it's okay. I can. The way the proof works is he defines like a relaxation, right? So slice rank has this combinatorial definition, and he defines like a sort of analogous to like fractional vertex cover. He defines like a fractional slice rank. That's not how he defines it, but it's equivalent to something like that. And then using geometric invariant theory, he shows that right, for that notion, if something has large relaxed slice rank over the base field, you can get like an F-rational proof of that, as evidenced by a certain polynomial not vanishing. And then that's proof that the slice rank is also large over the field extension, which is very interesting and useful to us, because then that shows that if we have a small slice rank decomposition over the extension, it's also small over the base field. So now we just chain together everything we've done. The slice rank over the base field is bounded by the slice rank over the closure, which is itself bounded by 3 times geometric rank. The 3 here is 3/2 times 2. Okay, that is then bounded by the analytic rank using the Schwarz-Zippel lemma and the point counting. And then we get 8.13 by plugging in size of f equals 3, because the smallest possible number besides 2. Smallest number bigger than 2. And that's it. That is the completion of the proof. So okay, I'm just about done, but I'll just sort of state this extended theorem, which we proved more recently. And what's going on here is Dirksen's lemma fails miserably for higher order tensors, at least as far as we know. We asked Dirksen, and he thinks so too. So we need something else. And so, right, we bypass Dirksen's lemma at the expense of a dependency on the analytic rank. So we need the field size to be large relative to the analytic rank. But in a lot of applications, this is a pretty reasonable thing to assume, because you're generally interested in the case of large bias. And so this theorem, essentially settles the structure versus randomness question for polynomials over large enough fields. If you have a polynomial and it's over a large field, then large bias, you can explain all of the bias in terms of partition rank, in terms of this decomposition into a few structured pieces. I was mentioned it's been conjectured by other people, and I don't really know why it took this to be true, but other people have conjectured it, that the partition rank is stable under field extensions as well. So if this is true, then the proof is much easier, and it doesn't depend on the field size does not depend on analytic rank. Okay, that's all I have. Thank you, Guy, for mentoring me, and the Discrete Math RU for hosting me.
Great, thanks a lot, Alex, for your very interesting talk. Are there any questions?
Alex, so I'm a little bit confused about the thing you said at the end about what what is not known for higher tensor versus 3 tensors that you proved. So, for example, other than so you require fields to be large. So let's just take that as a given. But it seems that at least qualitatively, what you have here is the same type of theorem as what you had previously.
Yes, exactly. It's the right analogy for higher order tensors.
And you can also squeeze this geometric rank in the middle.
Yes, exactly. This also goes through geometric rank, right? So the tricky part. So there's some proof partition rank is bounded by a constant times geometric rank, which also relies on derivatives. It organized in a different way, but it relies on derivatives. The difficulty there is you really need to choose a point on the variety that's like non-singular and stuff like this. And so the issue you run into is that it could be that there's no F rational points on the largest dimensional component that have this property. So the issue we run into is, so at first we tried using Langevin to sort of say there is a good point. The problem we ran into is that it's really hard to do that without getting a dependence. Every time we did that, right? Because Langevin has a dependence on the number of variables, we always had a dependence on the number of variables, which we didn't want. So instead we go about this by sort of looking at subvarieties that are nice in some way and sort of iteratively descending to smaller subvarieties that contain all the F rational points, and only using Schwarzschild, never Langevin, because we don't want the dependence on variables.
Well, if not, well, thanks a lot, Alex, and good luck with your PhD. I think it's